In the year 3026, on board the Dynasty 57.
My god, have you lost your mind, Job? Making a video while all that is happening around you? And how could something like that even happen with all that so-called world-class engineering?
Yeah, no extent of engineering could save any spaceship from this.
Logging into database. Job's loading.
Well, anyway, how are you, Satara? How's it going on Earth?
Same old.
Trajectory update.
Nothing special, just finishing off my thesis.
Nice. The history of neutron star research,
Yep.
right? And how's...
What the hell? I swear you need to come back home, Job's clerk.
I'm perfectly fine.
Being on a spaceship that has all its technology fried and has been hijacked does not sound fine to me.
Okay, who said it's been
A
hijacked?
ship does not change its trajectory automatically and willingly start heading towards a goddamn star.
Look,
Marshal troopers will be patrolling the ship, following recent suspicions of the presence of the extremist group Astronomical Angels on board.
I'm going to go get a coffee.
Yup, you heard that right. Almost all of this ship's electronic equipment has malfunctioned, and it indeed seems to be heading straight towards a goddamn star. The same star responsible for glitching the electronics. And it's not just any star, but a star that was born from the death of another. A neutron star. This menacing stellar oddity is formed only when a super heavy star, 8 to 20 times the mass of the Sun, collapses in on itself. When the force produced by nuclear fusion inside its core cannot match the immense pull of its own gravity, all of its atoms, including the particles inside these atoms, called protons, electrons and neutrons, violently smash into each other. This leaves behind only the neutrons, which are squished into a sphere roughly half the diameter of Melbourne. This is significantly smaller than a typical star, and much smaller than the largest asteroids, but with as much mass as a gigantic star. If this ends up being no heavier than 2.8 times the mass of the Sun, it explodes, leaving a neutron star. But how could a neutron star glitch the electronics of my ship, you may ask?
Well, neutron stars can be a source of highly powerful radiations, which in fact relates to how they were discovered. Before that, it was Walter Baade and Fritz Zwicky who proposed their existence for the first time in 1933. 34 years later, that led to Jocelyn Bell Burnell and Anthony Hewish to Cambridge researchers detecting regular bursts of radio waves from a region of the Milky Way. Who else could be sending such radio pulses, if not aliens? That was the initial assumption, which ended up with the source being nicknamed Little Green Men 1 or LGM-1.
They soon realised the true source of this radiation, however, and exactly what it was that they'd discovered. Not aliens, but a neutron star. But how? And how do we know that neutron stars are made of nothing but neutrons? And what happens next, after a neutron star is born?
Marshal troopers patrolling the ship.
Astronomical Angels on board.
To demystify these mysteries and many others, I'm contacting Rowena Nathan, an Earth-based astrophysicist from the year 2024 at the School of Physics and Astronomy at Monash University. She specialises in something called multi-messenger astronomy, as well as the timing of these radio-emitting neutron stars.
hello Rowena. Thanks for joining us today. How are you?
I'm worried about your spaceship, but doing well otherwise. Yourself?
Well, I'm feeling rather curious today. How do we know that neutron stars are made from just neutrons, and what characteristics set them apart from other stars?
We actually don't entirely know that neutron stars are made from just neutrons, but the thing that sets them apart from other stars is their density, and that also gives us a hint as to what they're made from. As far as we understand matter, the only thing that makes sense would for them to be made of neutrons. They're so dense that the protons and the electrons get smashed together into neutrons. And the other characteristics that set them apart from other stars is how fast they're spinning. Many of them spin very rapidly, It's like when you're an ice skater on ice and you bring your arms in. As the neutron stars collapse, they begin to spin faster.
I see. So, given these characteristics, do we use these to categorize types of neutron stars?
We certainly do. So the first thing we use to categorize neutron stars is their spin period, so how fast they're spinning. So we have slower spinning neutron stars, which also happen to be magnetars. Not only do magnetars spin slower than other neutron stars, but as their name suggests, they have extraordinarily strong magnetic fields. So up to 1 trillion times the magnetic field on Earth. I don't think you can even imagine the kind of effect that these would have. And then we have your garden variety pulsars, which have periods of around a second. And then we have millisecond pulsars, and they're really interesting because we can use them as clocks. They used to be more accurate than atomic clocks, but atomic clocks got really good. So we can use them for measuring time, which is really interesting. We also have categorizations depending on the emission they give. So we have pulsars, which usually emit in radio, but there's also X-ray neutron stars and gamma-ray neutron stars. So neutron stars can fit into multiple categories at the same time, and one example of this is pulsar Swift J1818-1607, and that's actually a magnetar and a pulsar, and the neutron star that your ship is headed directly into.
Oh, damn.
Oh, indeed. Job has good reasons to fear neutron stars, in particular pulsars, as they're the epitome of the strangest cosmic enigmas. They piqued the interest of Anthony Hewish and Jocelyn Bell Burnell in 1974, the same researchers who thought they'd found little green men, but were later celebrated for their work, with Hewish receiving a Nobel Prize. Burnell being left out was completely unfair, if you ask me, but both eventually received credit for their discovery of pulsars. 8 years later, Don Backer and his colleagues discovered a pulsar so maniacal, spinning more than 600 times per second, that it unveiled a completely new class of neutron stars, the millisecond pulsars Rowena mentioned earlier.
Okay, so spinning freakishly fast, being scarily dense, and even having overpowered magnetic fields, but that's barely the tip of the iceberg. Neutron stars can also undergo glitches and starquakes. Rowena, what exactly are these?
So I mentioned earlier that we can use neutron stars to measure time. So usually their rotation is extraordinarily regular, but sometimes they glitch and they suddenly spin up and start spinning faster, and we don't really understand why. One of the mechanisms we think that could cause this is a starquake. Similar to an earthquake on Earth, the neutron star crust cracks, releases some angular momentum, and it speeds up. These are extraordinarily energetic events, so they not only release some angular momentum, but a lot of other energy can be released too. So glitches could be caused by starquakes, but we also think it could be caused by something called a vortex avalanche. So the inside of pulsars are really interesting, and we think that the superfluid inside has quantized angular momentum. So if you know anything about quantum mechanics, you can only have certain energy levels. In pulsars, they can only spin at specific speeds. So the crust can spin at any speed though, and so a shearing force builds up between the two layers, and then at some point the vortices, which is what gives it that quantized spin, unpin, and we think a starquake could also happen at the same time, and it's this huge energetic event that causes the pulsar to spin up.
Wow, that's very interesting. You were studying the Vela pulsar during its 2016 glitch. Did your research lead to any new insights on the nature of these glitches?
Yeah, so the 2016 Vela pulsar glitch is actually really special because it's the only time that we've watched a pulsar glitch in real time. Hopefully coming from the future, you've seen a few more since then.
Oh, I've seen 5 or 6.
Oh my golly gosh, well I'm curious to see what they told you. But we indeed think that starquakes happen during pulsar glitches, and given they're so energetic, it's likely that a starquake could release a flare. And the starquake that just happened on Swift J1818-1607 could have damaged your spaceship, Job, and the electronics might not be working.
That's exactly what I suspected too. At least we can be grateful that it's a single neutron star, not a pair of pulsars orbiting each other. Remind me when those were discovered, Sitara?
2003 by Italian astronomer Marta Bergè. All these discoveries highlighted how far astronomical observational technologies had come since neutron stars were first proposed, which brings us to 2024.
Rowena, one of your areas of research is multi-messenger astronomy. What precisely is this, and what are the ways in which multi-messenger astronomy is currently being used in neutron star research?
So multi-messenger astronomy is when we have two messengers or signals. So we have signals from the electromagnetic spectrum, so that could be light, radio, gamma rays, and then we also have a signal in the gravitational wave spectrum. Gravitational waves were first discovered in 2015, so it's a really new area of research. One of the greatest unanswered questions about neutron stars is their equation of state. So how does their density relate to their radius? And using multi-messenger astronomy from the merger of neutron stars, so we can see the gravitational waves that come from the merger, we can better understand the equation of state and better understand what neutron stars are made from.
And how do you think this research might change in the future?
Well, once we can better understand how the matter inside neutron stars behave and what it's made from, this can actually give us insights into the universe just after the Big Bang, because it was really dense then. We don't exactly know the value of Hubble's constant, which is how fast the universe is expanding, and multi-messenger astronomy can help us to understand that better as well.
Thanks, Rowena, for joining us today. It was a pleasure to have you.
Yes, you're right, Satara.
Pardon?
This ship is not in the gravitational field of that neutron star. Changing its trajectory to head right towards it could only be achieved by hacking into its system.
You're coming with us.
No, you can't
Yes, we can. You really thought you could just change the damn ship's course and nobody would notice, huh?
What are you talking about? What are you...
My voiceovers were by Tristan Clonan, and Satara was played by Amanaka Sahu, while Eliza Moylan led the research, and Kushla McDermott was a liaison into the cover art. And we're all grateful for Rowena, Nathan, and her time. Amale Joshi directed this podcast and did the sound design, while I wrote it with him. Thank you. Thanks for listening.